Modern smoke detectors contain the radioactive isotope americium-241 with 95 protons and 146 neutrons. This isotope decays according to the equation. Americium-241 yields neptunium-237 plus a helium nucleus. The figure below shows the two decay products, which we will approximate as simple uniformly charged spheres whose radii are labeled in the figure. We are to calculate the electric potential energy of the initial configuration, and then, assuming that the neptunium nucleus remains stationary, which because of its very large mass is almost true, we must then calculate the velocity of the helium nucleus once it has moved far away. This is a classic energy problem, and as with all energy problems, we need to define the moments. The initial moment is when these two nuclei are next to one another and are stationary, and the second moment is much, much later when the large neptunium nucleus, which we assume is still stationary, is very far separated from the now quickly moving helium nucleus. We will connect moment 1 to moment 2 using the principle of conservation of energy. And this principle is realized by taking the total energy at moment 1 and setting this equal to the total energy at moment 2. In first semester physics, we knew of 4 kinds of energy to add into the total. Now that we're in second semester, with the advent of electric potential energy, we know of 5. So therefore, we look at moment 1 and recognize that there is no kinetic energy of translation, there is no rotational kinetic energy, there is no significant gravity, no springs, but there is electric potential energy. Accounting for the electric potential energy is the part of this problem that most students have some difficulty with. Whenever you see a collection of charges and you ask yourself what is the potential energy associated with this collection, regardless of how the collection came to be, we can actually get the correct result by imagining the process of assembling this charge distribution, moving all charges from infinity into where they are. And so for this reason, we can imagine a two-step process. Let's imagine that we first bring in the neptunium, and then we follow this with bringing in the helium. If we have brought in both of these two charges, we have completed the charge configuration and will get the correct value for the total potential energy of configuration at moment 1. Finally, to complete conservation of energy, we recognize that at moment 2, because these two nuclei are separated by a very large distance, the electric potential energy is negligible, so all we have is the kinetic energy, and in particular, this is the kinetic energy of the helium nucleus, which is moving at some unknown velocity that we will call V2. Let's deal for a moment with the two energy terms on the left-hand side. First, we imagine bringing in the neptunium when there is no other charge at the location. Because there is no other charge around, there is no potential, there is no force that you have to work against to bring in the neptunium, and so, as with all charge configurations, the very first item to show up requires no work or energy to put it in place. The only thing that we'll need to account for in getting the total energy of the system is to imagine the QV, in this case it is the charge of the helium, being placed at a location whose potential is defined only due to the neptunium. That will represent the total potential energy at moment 1. You might validly ask why I chose to assemble this system in the order of first the neptunium, then the helium. What you'll see in a moment when we look at the final answer to this problem is that if you were to have assembled the system in the other order, you would have come up with mathematically the identical amount of potential energy on the left-hand side of the equation. So no matter which order we assemble a collection of charges, we always get the right answer for the potential energy. The charge of a helium nucleus, which has 2 protons, is going to be twice the elementary charge E, and the potential due to the neptunium is going to be K times the charge of the neptunium, which is 93 times the elementary charge, divided by some distance r. We're going to need to look closely at our figure to understand what this distance r represents. The helium nucleus has been placed at a particular location and experiences the potential of that location. Because this location is outside of the much larger neptunium nucleus, we are correctly treating the neptunium nucleus as though it was a point charge. What we can see is that the distance r, as represented in this figure, is the distance between the center of the neptunium nucleus and the center of the helium nucleus. In this case, we will take our 7.4 Fermi, we will add it to the 1.9 Fermi, coming up with a total distance of 9.3 Fermi or femtometers as the value of r that we will place inside our calculation. Returning now to the calculation, we see that we have twice 93 times the electric constant K, the elementary charge squared, divided by 9.3 femtometers. If we plug in all of the appropriate values and recognize that femtometers represent 10 to the minus 15 meters, if we do our algebra correctly, we find that the left-hand side of this equation is 4.614 times 10 to the minus 12 joules. And this value on the left-hand side of the equal sign is in fact the answer to part A of the problem. To solve for part B of the problem, all we need to do is substitute in the mass of the helium nucleus. Since a helium nucleus contains 4 particles, 2 of them are protons and 2 of them are neutrons, and the proton and neutron have roughly the same mass, we're able to approximate the mass of the helium nucleus as 4 times the mass of the proton. Using the value for the mass of the proton as given in the table in this problem, we can then solve for the velocity at moment 2. We get the result of 3.71 times 10 to the 7 meter per second. This is in fact not all that large of a velocity for a particle. It is on the order of 1/10 of the speed of light, and so this particle is in fact non-relativistic, and so to most particle physicists this is considered to be a slow-moving alpha particle. Finally, the last part of the problem notes that the velocity necessary for a particle to escape from the planet Earth is actually 11,000 meters per second, much smaller than the previous result. However, despite this, you receive virtually no radiation from your smoke detector. And the reason is very simple. An alpha particle with this low in energy actually doesn't penetrate more than about 4 centimeters worth of air. That's why this alpha particle doesn't leave the planet. In fact, it doesn't even leave the smoke detector.